Hello friends, my name is Sabrina Lewick and this presentation is on wine faults and it is prepared for students at the Institute of Masters of Wine. For those of you that don't remember me, that's me over there on the left wearing my super cool Breaking Bad lab goggles. Hi there. And over on the right is my beloved Digby, and I just threw him in there for fun because why not? So here's a recent question, or somewhat recent question from the Master of Wine exam, and it was also on one of our recent TAMs. How might the most common faults in finished wine be avoided and detected? And this is what the examiner's report had to say. They actually wrote up quite a good amount on this, but I highlighted a couple important sections here. They highlight that a number of answers failed to mention how the faults could be detected despite an excellent discourse on their avoidance. And also they mentioned that candidates should have refrained from referring to corky taint. And I put this in here in a highlight because I want to differentiate between wine faults and taints that can be acquired in the finished product. So today we're not actually going to talk about cork taint or things like light struck or anything that can happen after the wine's bottled. This will all be things that are required in the winemaking process. And we'll definitely put a focus on the detection of these faults as well, because it seems like there was a little bit of a deficiency there. And I'm always prepared to admit when my shortcomings or where my shortcomings are. And I'm not a lab analyst. I don't work for ETS laboratories. So I know how we can detect these things, but I can't tell you intimate details on the mechanisms of some of these analytical processes. And there are many faults out there. And one of the recent questions asked specifically for common wine faults. So I've divided these things out into common wine faults and less common wine faults and given a pretty similar detail for each of them though. So we're going to go through on the common and look at oxidation and reduction. Those are two things that kind of go together. Volatile acidity and Brettanomyces aromas. And then less commonly, diacetyl, smoke aromas, mousiness, geranium aroma, sulfur dioxide aroma, and re-fermentation. So I really like this old adage here. I think it was originally attributed to Paracelsus. Oh man, I gotta look that guy up. But basically it was in 1500. And the adage is, it is the dose that makes the poison. So really anything can actually be a poison in high enough doses. And the reason that I want to start out with this is one of the things that I included actually in a little recent essay I did on this, because many of these things that could be considered faults at sufficiently high or at extremely high levels can be considered to be complexity or desirable components at a lower level. So I think that this is important to mention. Only a few of these things have a hard yes, no, fault, not fault. Many of these things only become a fault at a certain high level or high concentration. And another important adage is an ounce of prevention is worth a pound of cure. So today we're going to talk about both prevention and remediation, because it's much better to actually prevent these faults from happening in the first place than having to remediate them after the fact. So let's start out with some common wine faults. Before this, I'm just going to give a really brief lesson here on redox. And you can see that this word is the word reduction and oxidation smushed together. So the redox potential is the ability of a system to act as an oxidizing or reducing agent. When we have wines, wines are a reducing medium. So things naturally want to be more reduced than oxidized inside that system, which is why we can get reduced off aromas during fermentation. We'll talk a little bit more about that. So during winemaking, oxidizing and reducing compounds are added and removed from the wine. So the main oxidizing agent in wine is oxygen, which is acquired from oxygen contact. And we have multiple reducing agents in our wine. They can be things like phenolics, tannin and color, sulfur dioxide, naturally occurring glutathione. So there's quite a few things here that act as reducing agents or antioxidants. So moving on into the meat of our presentation here, I've tried to structure this presentation around one of the questions that we had recently, including detection and remediation. So most of the slides here are going to include a table that shows source, sensory impact, detection, prevention, and remediation. So we're going to start with oxidation here. And oxidation, the source of it is oxygen contact with wine. So our sensory impact on whites and reds is browning, but it's much more evident in whites. Decreased varietal aroma in whites and reds, but it tends to be much more evident in whites. You've probably experienced this as a wine consumer and wine professional, but when you have the oxidation of varietal aromas, you tend to have just a scalped aroma, or even sometimes things can smell like not musty cardboard like cork, but just kind of like a fresh sheet of paper, just nothing. On the extreme end, we can get oxidized aromas of acetaldehyde, which smells like bruised apples or nutty or sherry-like, and this occurs in both whites and reds, but it's still much more common in whites because in reds, the tannins can bind up with acetaldehyde, whereas in white wines, the only thing to bind to it is sulfur dioxide. So to detect oxidation, we can either analyze for free sulfur dioxide or acetaldehyde. It's much, much easier to analyze for free sulfur dioxide and to use that to infer oxidation instead of looking directly at acetaldehyde, which is produced during the oxidation process. So every one of these faults that we're mentioning today, the main piece of equipment I start with is sensory. All of these things can be detected with your nose or your eyes or both. But for free sulfur dioxide, we can analyze our wine with aspiration oxidation and then subsequent titration to figure out how much free sulfur is in the wine. We can do something somewhat similar, analyzing free sulfur by Ripper method, which has iodine and a starch indicator. We can also use flow injection analysis or gas chromatography flame ionization to look at acetaldehyde. For prevention of oxidation, basically just avoid oxygen contact. When you're moving your wine physically in the winery, like pumping from out of barrel or from moving tanks, blanket and push with inert gas, so this includes nitrogen or argon, and keep your vessels topped up. Also keeping free sulfur dioxide levels at a safe level, usually that's over 35 milligrams a liter. And I've also mentioned here sparging with nitrogen. This actually, I put this way at the end because sparging with nitrogen is much more common right before bottling. It's a way of forcing dissolved gases, including oxygen, out of our wine, which could have an oxidative process in bottle. But that's a less significant point than our other ones, including avoiding oxygen contact. And remediation for oxidation, if there's still time, sulfur dioxide addition. This sulfur dioxide will bind directly to the acetaldehyde and make it not sensory detectable anymore. If the wine has browning in it, what you can do is fine away those small brown compounds using a proteinaceous fining agent, or PVPP is another option. That's polyvinyl polypyrrolidone. And you can remove some of the brown compounds. Something of note here is that oxidation and volatile acidity tend to go hand in hand. These examples here don't include VA, and we'll talk about VA on its own a little bit later. I also haven't mentioned intentional oxidation of white juice here, which is can be used in certain styles, including Chardonnays. And I haven't mentioned intentionally oxidative styles either. If you take a look at that examiner's report, they thought that a good answer included the mentioning of intentionally oxidative styles. So we just haven't addressed that here. Moving on to reduction. So there's a couple different types of reduction to look at. The simplest form of reduction is simply hydrogen sulfide, and it's easy to remove from the wine. Complex reduction is much more complex. It's what happens when that hydrogen sulfide reacts with other compounds in our wine and forms other aromatic compounds. And these things can be quite difficult to remove. So we can have mercaptans or thiols. Mercaptan's a very common term, but it's more, I'm trying to think, the word's not appropriate, but it's falling out of favor, and thiol is a more appropriate term to use now. So this is a broad term of aroma compounds that contain a sulfur group, SH, and they can smell like cabbage, garlic, onion, rubber. And disulfides are another related compound, and they're oxidized mercaptans or thiols, and some of them can smell like burnt rubber or garlic. So detection and remediation for simple reduction or complex reduction is the same regardless of how the reduction got into the wine in the first place, because these compounds will just react the same regardless of where they originally come from. So here's some more details on how these forms of reduction can get into the wine and the prevention of them. So agrochemicals, sprays from the vineyard that contain elemental sulfur that are applied too close to harvest, they can cause reduction in a wine. And this is a pretty wordy table here, my apologies. To deal with that, or to prevent it in the first place, limit the sulfur use in the vineyard, or make sure that the timing is structured correctly so that you don't harvest too soon. The winemaker can rack off the heavy lees, basically the junk that comes in on the grapes before fermenting. And then additionally, early racking off of the yeast lees later. You're just trying to get the solids out of the wine as quickly as possible. Another source can be metal cations, including copper, iron, zinc, and manganese. And these can come in on agrochemicals, or if a winemaker accidentally adds too much copper, maybe if they added copper early. So avoid late applications of agrochemicals and avoid copper additions during fermentation. Another main source can be inorganic sulfur, which for us just means sulfur dioxide. And what happens is that sulfur dioxide, if it's added during primary fermentation, it goes into the yeast cell body and then it's liberated as hydrogen sulfide. So the prevention of this is mainly yeast nutrition, feeding our yeast a proper diet of nitrogen, choosing a yeast strain with lower levels of sulfur dioxide production, or keeping the sulfur dioxide addition lower before fermentation. So, for example, the sulfur dioxide addition that happens at the crush pad. And a related thing here is organic sulfur that comes in from amino acids, including cysteine and methionine. What ends up happening is when the yeast are starved for certain nutrients, including cysteine and methionine, which are naturally low in grape must, what our yeast will do is they're going to scavenge sulfur-containing compounds and try and make these amino acids inside their bodies. So the result is the liberation of that stinky hydrogen sulfide. If a winemaker keeps their yeast well fed, there should be significantly less of this kind of reduction, or they can choose a yeast strain with lower levels of hydrogen sulfide production or lower levels of nitrogen requirements or sulfur requirements. The winemaker can aerate the fermentation as well. More oxygen makes for a happier yeast. And also managing native or wild yeasts up front. Yeast and bacteria can actually eat through the nitrogen in our juices and musts that are destined for our preferred yeast. So if we manage the other microbes present, they're not eating the food that we want to give to our yeast. So here is some wordy stuff right here. Reduction, detection, and remediation. The compounds involved in stinky reduction, I actually just did a copy and paste from ETS, so thank you very much. Compounds include carbon disulfide, methyl thioacetate, ethyl thioacetate, diethyl disulfide, diethyl sulfide, dimethyl disulfide, dimethyl sulfide. I feel so silly reading this all out. Ethyl mercaptan, hydrogen sulfide, and methyl mercaptan. So the equipment for this, just like with the oxidation, use your nose. You can smell these really easily. Our bodies are really great at detecting compounds that are poisons to us, and they make so these kind of compounds can exist at very low levels, but we can detect them with our nose. Another method for this is sulfide analysis using gas chromatography mass spectrometry. For remediation, for simple hydrogen sulfide, the addition of copper sulfate works. It binds up to the hydrogen sulfide and forces it out, basically drops it out of the wine. For complex reduction, which is everything on that list except for that hydrogen sulfide there, copper sulfate and ascorbic acid is required. Basically, the ascorbic acid breaks the bond between the hydrogen sulfide and the other compound, and then the hydrogen sulfide can be removed. This process only works in the presence of sulfur dioxide, so you have to have sulfur dioxide in the wine for this to work. Moving on to volatile acidity. There are two main components involved in volatile acidity: acetic acid, which smells like white vinegar, or ethyl acetate. And this is the result of acetic acid reacting and esterifying to ethanol. And it has a nail polish remover type aroma, and its detection threshold is 25 times lower than acetic acid, which means it's 25 times easier for you and I to smell it. So here are two diagrams, one of acetic acid and one of ethyl acetate. And I don't really have a laser pointer here. I don't know if, oh yeah, I guess I can't do that on my computer. But the ethyl acetate, actually, those two lines next to the O, basically those are two carbons attached to that O right there, and that's where the ethanol esterified to the acetic acid. For volatile acidity here, we're going to look at sources and prevention. And then we'll talk a little bit about detection. The detection is pretty similar for all these different sources. So we can get volatile acidity formed at crush by spoilage yeasts that are converting sugar into ethyl acetate and acetic acid. One of the main species involved here is Hansenii aspera. The prevention of this is to add sulfur dioxide at crush or to quickly inoculate with Saccharomyces cerevisiae before these things get a foothold. Yeast can also produce volatile acidity due to osmotic stress, and that means that they're in a high sugar or high Brix environment. And also they'll produce volatile acidity if they are getting stuck. Usually this happens below 8 Brix. So the species is Saccharomyces. And the prevention of this, if it's legal in the winemaking area, you could add water to lower the Brix and lower the stress, or you could choose to pick earlier if that's in line with the style of the wine. Lactic acid bacteria can also produce volatile acidity. This includes Enococcus and other lactic acid bacteria. They will do this if they are fermenting malic to lactic acid in the presence of residual sugar. They turn that sugar into volatile acidity at the same time as they're turning malic acid into lactic acid. So the key to prevent this is ensure sugar dryness before malolactic. So make sure your wine is dry before you start. And spoilage bacteria during the aging process can also produce volatile acidity. These are usually Acetobacter or Gluconobacter, converting ethanol into acetic acid. And these bacteria all require oxygen to do their job. So if you keep your vessels topped up, this should halt that process. And I don't take any credit for this awesome little diagram here. This comes from my coworker, and I wanted to show it to talk a little bit about stuck fermentations and yeast stress. So he found this diagram called Death on the Mountain, and it's talking about climbers on Mount Everest and how you have significantly fewer deaths below 8,000 meters, and between 8 and just under 9,000 near the summit, that's where the death zone is. Huge amounts of people die up there, and it's very similar to bricks and yeast. So if we're at 18 bricks, which is something that would be like a sparkling wine, you might have a stuck fermentation every once in a while, but it's very rare. Getting up to 21, they become a little more frequent. And 25 is really where the line starts to happen. And once we're over 25, up at 27, which is actually quite common for really cranked up high octane reds, you have a significantly higher risk of stuck fermentation. And in those situations, like between 25 and 27 bricks, that's the area where, well, we have the risk of stuck fermentation. And even the successful yeast, they're stressed out because there's so much sugar around them and it's sucking the water right out of their bodies, actually. And they produce volatile acidity as a stress marker. So the detection of volatile acidity. The two main compounds, like I said before, are acetic acid and ethyl acetate. So the equipment for detection could be sensory, again. Acetic acid can be analyzed through multiple different methods. The really old school method is cash still. It's basically a steam distillation. You boil water around the wine sample, and because the surrounding chamber has steam in it, it's hot enough to force out the acetic acid, and it can be distilled and then titrated. The more modern technique for this is enzymatic. You can have enzyme kits that can detect acetic acid in a similar manner that you can detect residual sugar or malic acid in a wine. And there can also be direct ethyl acetate analysis through GCMS. I spelt that wrong there. I was looking at that. I'm like, what did I write? GSMS. I meant to write gas chromatography mass spectrometry. And remediation. Blending away is an option if you have a significantly lower VA lot that's stylistically appropriate to blend. You can blend your high VA wine with the low VA and get to a level that's more appropriate. Another way to deal with it is nanofiltration with a specific acid cartridge. So nanofiltration is like filtration at a crazy high level. You actually have molecular weight cutoffs. The pores are so tiny that they only allow individual molecules to go through that are under a certain size. And the good news is that acetic acid and ethyl acetate are teeny molecules. So they'll slip through and other compounds will continue on by, including the majority of aromatics. And then that permeate that's forced through, the stuff that has a bunch of VA in it, it gets passed through a column or a cartridge that specifically binds up that acid, and then that permeate can be reintroduced into the wine. You can get a 30 to 40% reduction in volatile acidity with each pass through that filter and cartridge. Moving on to Brettanomyces related aromas. So these all come from Brettanomyces. Looking at the sensory impact, there's a couple different compounds, or actually 3 different compounds we're mainly looking at. 4-ethylphenol, 4-ethylguaiacol, and 4-ethylcatechol. And they all have different sensory impacts or aromas. The detection of these compounds can be with your nose or through GCMS. You can't do old school wet chemistry for this. You need some pretty advanced equipment. And the prevention of this is sanitation and running your cellar cold. Brett is really quite resistant to both sulfur dioxide and ethanol, whereas most other things that cause spoilage in our wine are much more susceptible for these things. So the main way to deal with Brett is sanitation of equipment and containers that the wine could be stored in. if possible. It's actually not possible to really sanitize a barrel because it's porous, but cellar crews can steam them really sufficiently. And then running the cellar colder. So an example here, a local winery in Walla Walla had a Brett outbreak, and the remediation process was the full racking out of all of the lots that had been infected. The lots were then sterile filtered, the barrels were individually steamed, and then the wine was put back into those barrels. And the cellar was moved from 55 degrees Fahrenheit down to 52 degrees Fahrenheit. And that winery hasn't seen increased cell counts since. The remediation of Brettanomyces related aromas can be nanofiltration with a phenol absorbing column. So if you remember that volatile acidity slide we had last talking about the VA removal in the nanofilter, it's a very similar process. You just have a different column that the permeate is passed through. Or if the wine is sterile filtered and then blended with another wine, it could cause a reduction in the concentration of the aromas. And because the wine has been sterile filtered, you know it's not going to bloom again and produce more aromas. So Brettanomyces cells, not specifically Brettanomyces aroma, can be detected through sterile plating. Another method is the scorpions analysis that ETS does. It's a proprietary method that looks at DNA that's floating around in the wine. Something to note here is that the presence of cells doesn't necessarily mean the presence of that characteristic bready aroma. The yeast cells actually have to get up to a certain quorum or concentration before they start making these aromas. And also different strains of Brett have different sensory impacts. Some are more weighted towards 4-ethyl catechol or maybe 4-ethyl phenol. So not all of these things behave in the same manner. And now moving on to less common wine faults that are still worth discussing. Diacetyl here. The source of this is Enococcus, and actually I should have put, there can be multiple lactic acid bacteria that form diacetyl. That's my mistake for putting Enococcus as the only source, but I have put that as a note below in red. Diacetyl has, at a lower level, like a 1 to 4 milligram a liter, kind of has a buttery aroma, which can be pleasant, but at higher concentrations, it can smell more like sour cream or spoiled milk. To detect diacetyl, you can use your nose, or you can use GCMS. The prevention of diacetyl is don't undergo malolactic fermentation in the presence of citric acid. That actually is a desired style for some people, and they would do a citric acid addition and then undergo malolactic fermentation. It's why Rombauer tastes like Rombauer. But if you don't want that diacetyl, make sure that you're not undergoing malolactic in the presence of citric. And if you haven't directly added citric to your wine, a source of citric in the winery could be sanitation liquids. The remediation of diacetyl taint is sulfur dioxide addition. The free sulfur dioxide actually binds up to diacetyl and renders it aromatically non-detectable. Smoke influence, which is a pretty hot topic these days and is very difficult, or actually right now it looks like it's impossible to remediate. So smoke influence, the source is smoke in the air during the growing season, and these volatile phenols enter the grape berry via the waxy cuticle on the outside of the grape. And the sensory impact usually isn't very pleasant. There might be a light smokiness, but frequently things can smell medicinal, burnt, or ashy, like cigarette ashy. The detection, you can look directly at guaiacol, 4-methyl guaiacol, or cresols using triple quad GCMS, or sensory, again, but that's, not empirical. The prevention of this is basically we have to stop global warming so that we're not having brush fires and other forest fires near grape growing regions. If a winemaker suspects that they have smoke influence in the berry, they can minimize the skin contact in whites and reds because a lot of these compounds are in the skins. For remediation, unfortunately, there's no real permanent solution right now. The real difficult thing about smoke is that these compounds bind up to sugars in the grape berry. So what you'll have is a little smoke compound, and then it'll be attached to it, maybe a short chain of sugars. So 1 to maybe even a dozen sugars. And what happens is that smoke compound doesn't smell like anything yet because it's bound to all those sugars. But during the winemaking process or aging, those sugars can start unbinding and popping off. And eventually the sugar chain will be run down and that smoke compound is liberated, and now you can smell it. So it's really difficult to figure out what to do here without having a really serious impact on wine quality, because you could remove all the smoky aroma from your wine through a couple different methods, maybe reverse osmosis, or maybe carbon fining, which is the nuclear option, which then would remove a lot of other flavors from your wine too. But that doesn't guarantee that you don't have more smoke attached to a bunch of sugars in your wine that's still waiting to come out. So right now, there really is no true remediation. Moving on to mousy aromas. Oh, it's a cute little photo of a mouse there. The source of this is heterofermentative lactic acid bacteria. So usually these are spoilage lactic acid bacteria species that come into the wine due to sanitation issues. And the sensory impact of this can be like a caged mouse aroma, so like the shavings that you keep in a mouse cage, or cracker biscuit. And these are flavors, not aromas. And this is worth mentioning because these things actually, they're not aromatic, but they're liberated by your saliva in your mouth. So you don't smell them, but once you put it on your palate, they can be liberated. And I don't think I've actually seen any analysis for these specific N-heterocyclic, I believe is the name of the compounds. So mainly right now it is sensory. And the prevention of this is quick, clean malolactic fermentation with your preferred Enococcus species. And unfortunately, right now, there's no remediation. I've actually pulled in a quote here from the Australian Wine Research Institute. So they said that the AWRI observed an increased incidence of mousy wines during the 90s when winemakers moved to a low sulfur dioxide regime for the production of red wines in particular. Many red wines and some full-bodied white wines had no sulfur dioxide added until the completion of malolactic fermentation. So those low sulfur conditions allowed those spoilage lactic acid bacteria to get in. Next we have geranium taint, which isn't very common in professional wines or commercial wines. It's much more common in actually home wines. And the reason for that is because of the use of sorbic acid, which is an anti-yeast agent that can be used quite frequently in sweet wines, in wineries or homes that don't have the ability to sterile filter wines. So the source here is lactic acid bacteria transforming that sorbic acid, and the resulting compound smells like crushed geranium leaves. This can be detected with GCMS, but usually for things like this or for the mouse taint, it doesn't really make a lot of sense to spend that much money on something you can detect pretty easily with your own nose. To prevent this, the winemaker should have appropriate sulfur dioxide levels so that lactic acid bacteria don't grow, and don't use sorbic acid. There's a lot of other agents out there instead of that you can use for anti-yeast activity. And unfortunately, there is no remediation for this, except for maybe blending away. The last thing we're going to look at today is sulfur dioxide. And this is the overwhelming aroma of sulfur dioxide in a wine, and it's related to the sulfur dioxide concentration and wine pH. And it's not the same as sulfur reduction. Here's an example showing some numbers illustrating how pH can impact molecular sulfur dioxide. For those of you that have been following these presentations, you can learn more about molecular sulfur dioxide in the SO2 presentation. So this is actually looking at that same Dunhoff wine that we looked at in that previous presentation. The pH is 297, the free sulfur is 31 milligrams a liter, and the molecular, as a result, by calculation, is 2.01 milligrams a liter, which is very detectable. And if this winemaker had maybe made the choice to use less sulfur dioxide, like 10 milligrams a liter instead of 31, the molecular would have been down at 0.7, which would have been much less aromatic. But this is a stylistic choice for ageability, so I'm not here suggesting at all that this is a taint. But what I'm trying to do is illustrate that pH and free sulfur dioxide are linked in the making of this very aromatic sulfur dioxide that's the molecular form that really smells like a struck match. So usually it's the source of the sulfur dioxides are either the over addition of sulfur dioxide or math errors. It's really easy when calculating a sulfur dioxide addition to accidentally add 10 times too much. So the sensory impact of this sulfur is a burnt match aroma or the physical burning sensation in your nose. So good news is that this is pretty easy to detect with laboratory equipment. We can do sensory, aspiration, oxidation, which is the same method that I mentioned earlier for the oxidation. We can do Ripper method, which is the same as the oxidation, or flow injection analysis. For prevention of this, check your math before you do your sulfur dioxide addition and calculate molecular sulfur dioxide after selecting a free sulfur level. You might see that actually the molecular could be very high based on the current pH of the wine. And remediation, one could add hydrogen peroxide if that's legal in that country. The hydrogen peroxide binds directly to the free sulfur and makes sulfuric acid and removes the sulfur dioxide from the wine. If you've got time, the free sulfur will naturally drop, or the wine can be blended with a lower sulfur wine. The very final slide I have here is for re-fermentation. And this is Saccharomyces fermenting glucose and fructose that remain in the wines. And the sensory impact of this is the development of ferment esters, so the wine starts smelling like a ferment again, and the carbonation of the wine, so you'll start having dissolved CO2 pétillants in the wine. The detection, the compounds involved are ferment esters and carbon dioxide and sugar. So we could use sensory. We could use a carbodoser, which is actually an old school piece of equipment where you put your wine into a little cylinder that has a small cap on it. You put your thumb over it and you shake it. And the pressure of the carbon dioxide builds up inside that chamber. And when you remove your thumb, a little bit of the wine shoots out and it shows you how much CO2 is in the wine. So this could be used to figure out if you're increasing in CO2. You could do residual sugar analysis by enzymatic methods, or maybe a wet chemistry method like the old school Redox assay. For prevention of this, make sure that your wines are dry if they're intended to be that way, and maintain proper free sulfur dioxide levels in the wine during storage. I've put in brackets here, re-fermentation in bottle is related to sterile filtration. So that's not something that we're really going to talk about today because we're focusing mainly on things in the wine, not in, things that happen after bottling, or I should say things in the winery. And remediation of this, if the wine is undergoing fermentation, sterile filtering that wine to a sterile vessel will remove the yeast culture and therefore it will stop the re-fermentation. And then you can bump up the free sulfur dioxide level to something that's safe that will halt the fermentation. And this is all that I have for you today. I didn't include as many examiner report things as I did in the last presentation that I put up online. I'm looking to frame this less about the questions and more about just a really basic wine micro and wine chem lesson today. If you have any comments, please email me. People who have the link for this probably have my email address as well. Thank you very much for listening.